anytime something is moving around in a circle, even with its constant speed, immediately what you can tell that some of the forces on it are non-zero. All right? They'll only be moving like that if there is some net force acting on it. Okay? Now the question is, where does that force come from? In what direction is it pointing, and so on? Okay? There's circular motion, moving with constant speed in a circle. The speed is constant, the direction is changing. In what direction will the acceleration be? What would you say?
There are two directions, there's a two acceleration, one is forward to the center.
Okay, one second. This is based on things that you've learned before. I want to develop ideas based on intuition and so on. Okay, what would you say first is the direction of the acceleration? Let's say you have an equation. That equation gives you information. And from that, you can link the direction of the acceleration to something else. To what?
Forward.
To what?
Forward.
We know the direction of the acceleration will always be the direction of the force. We know that there has to be a force because it's accelerating, it's moving in a circle, it's changing direction. All right? So now the question is, what is the magnitude of that acceleration, and what's the direction of that acceleration? So what would you say, let's say, about the direction of the acceleration? The object is moving like this. What is the direction of the acceleration? In order to figure that out, we have to know what is the definition. What's the definition of acceleration? Change in velocity over the amount of time. Time is a scalar here. Time, in this case, does not have a direction. Of course, we all experience time having a directionality towards the future. The acceleration A is a vector, which is the vector delta V over a scalar delta T, an amount. Okay. Obviously then, what is the direction of the acceleration? Direction of the, not the velocity, but the change in the velocity. Now, when you're moving in a straight line, in which direction is your velocity? In that one. Let's say you're accelerating, in which direction is the change in velocity? Also that one. How about if you're moving fast and slowing down? Which direction is your velocity? That one. Which direction is your change in velocity? That way. Back. Okay, the opposite way. So the change in velocity is certainly not necessarily always in the same direction as the velocity itself. Right? Okay, that's a very important point. Now, in this case, where is the change in velocity? Let's throw off first the direction of the velocity. All right? At any given point, let's say the velocity is like this. At this point, it's going like that. At this point, it's going like that. Okay? What is the direction of the change of velocity? Okay, think about it carefully. And think about, it's not at all obvious, it's not at all intuitive, at first at least. And if you can't think of what it is, think how you would find it out. Okay, what does this mean, delta V over delta T? Why do we put a delta? And really what we mean in this, we discussed at the beginning of the semester, we really mean in the limit as delta T goes to 0, right? We want to take two adjacent points, 2 points which are so close together that this is extremely tiny and gives you an answer that's as accurate as whatever precision you're demanding, all right? So really what I have to do is think of 2 points that are very, very close together, not like this and this B and this B, but really I have to take, let me take a part of a circle, all right? And I'll take the velocity at this time, all right? And the velocity at this time. Okay, at 2 adjacent points. I can move vectors, I don't have to keep it here on the rim. I'll move it so that you can see it. One is, let's say, like this, right? And the other one is slightly bent. And the next one will be slightly bent, and the next one will be slightly bent, right? Slightly bent, slightly. Okay, so one will be like this. Draw it bigger just so you can see it. And the other one will be slightly bent relative to it. Now I can move that vector, it's just information, right? Doesn't matter where I put it, I'll put it here. Okay, I didn't change anything, just moved it. Okay? So now tell me, where is delta V? Okay, what direction is delta V pointing?
I guess it would be changing from the tip of one arrow to the next.
Okay. Delta V, by definition, means what?
The
The change means V2 minus V1. Okay? So this is the first one and this is the second one, so this is V1 and this is V2. How do you do V2 minus V1? It's V2 plus minus V1. So if this is V1, reverse it and you get minus V1. So we have, this is minus V1, right? So delta V is V2 minus V1, which is the same as V2 plus minus V1. V2 we keep the same, and we add it on to minus V1. So what is delta V? Just add the vectors. Okay, you see that? This is V1 and this is V2. V2 minus V1 is V2 plus minus V1. To detail. Okay, draw this in your book so that you have experience drawing. It's in your book, but draw it in your notebook just so that you have experience drawing.
That second one is V2?
Yeah, this is V2. And this is delta V. Okay, so delta V, in kind of an unexpected and a counterintuitive way, is pointing this kind of inwards. But now when you think of it, it makes sense. If V was like this and the next V is slightly at an angle, obviously it's the delta V that caused it to go at an angle. So the delta V is exactly pushing it down. Okay, pushing it down so that it's like this. Delta V pushes it in kind of, so it's like that. Do you see that kind of intuitively now? Why now after the fact you can see that if this is V, delta V obviously is pointing like this way. Because delta V is the thing that makes it become like this. In terms of forces, if something is moving like this, clearly, in order for it to later move like this, there has to be a force like that. Okay? So it kind of makes sense afterwards. You see something's moving like this, and then you see it's moving like this, and then it's moving like that. Obviously, there's a force pushing it in. Okay? Can you see that? All right? So it's possible to show, we won't do that right now, that in fact, delta V is exactly towards the center. You can kind of see it by symmetry because if it's going this way, you know it's pointing somewhere in, and if it's going that way, it's also pointing somewhere in. So it kind of makes sense in which direction should it be? Should it be like that or like that? It makes sense that if whatever way it's going, it goes in, then by symmetry it should go towards the center. Okay? And that's something that can be shown rigorously, but we're not going to do that right now. All right? So the direction of acceleration of an object moving in circular motion is towards the center of the circle. If it's moving in a circle, the acceleration is towards the center of the circle. Which means that where is the force pushing? Towards the center. Okay? A force that's pushing towards the center is given a special name. It's kind of misleading sometimes, but they use the name in any case. There's centripetal and centrifugal. Fugal means fugitive, like running away from, so centrifugal means running away from the center. Centripetal means towards the center. But it has no significance, it's just a word. It's not even a real physics word. So if you have something moving in a circle, clearly there is acceleration. Clearly the acceleration is toward the center, which means that obviously the unbalanced forces are towards the center. And in English, it's called forces towards the center is called a centripetal force. But it's not a certain kind of force or something. It's just Instead of saying a force is pushing towards the center, we say centrifugal force. So don't think of it as something.
The speed and the direction of the velocity is the same, but the acceleration is different because of time in which
Okay,
they do it.
the speeds are the same at any given instance.
Right?
The direction of the velocity is the same in the sense that it's always tangential to the circle. That their accelerations will always be to the center of the circle. But the direction towards the center or the direction on the tangent will be different at any given time today. Why would it be moving in a circle? If something is moving in a circle, clearly it has acceleration, clearly it unbalanced forces. Got to be some force or forces acting on it. Okay? So let's take an example of some force. It could be a planet going around the sun. It could be a ball on a string whirling around. Okay? What is the reason that the ball goes around and around? What force acts on it? So you have force of gravity going down, and so on, other things. But let's forget the up-down. In order to get rid of the up-down, let's consider that it's one of these chairs with wheels, and I tie it to something and I swirl it around me. Okay, so the normal force and the gravity force are canceling out. I don't worry about that. I'm just worrying about the motion like this. Okay, it's going around. Why is it going in a circle? If it's going in a circle, clearly I know that unbalanced force is acting on it. What possible unbalanced forces could be acting?
Pulling towards the center.
Pardon me?
Pulling toward the center.
Pulling towards the center, the rope. The rope is pulling on the chair. The reason that the rope is pulling is because I'm pulling on the rope. But if I look just at the chair, I see the rope tension pulling inwards. Any other forces?
The chair pulling
Okay, forces acting on the chair.
on the chair.
Which forces are acting on the chair?
The weight. Well, the chair wants to go that way too. So
Negotiating the ball.
tension.
Right, that's what you said, right? The answer is there are no other forces. There's the force of the rope pulling on it. There's no other force other than the up-down, which cancel out. There could be friction, but it's a wheel, so we're ignoring friction with the floor. Okay? So there's only one force, the force of the rope pulling it in. Because the rope is pulling it in, what direction is the acceleration? In the direction of the force, which is in. What happens when you take something, if something is moving, in order to start something moving in a circle, you have experience. If you just pull it, what will happen? It'll come towards you. Okay? How do you get something to move in a circle? You kind of throw it and then pull. Throwing it is what gives it the initial speed, gives it a certain speed. And then you pull. And what do you do when you pull? Do you pull it in the direction of motion? Do you roll it and then pull it like this? It'll just come back to you. Do you roll it and then pull it like this? It'll follow you. What you do, you kind of roll it and pull perpendicular. Okay? So it's rolling like this, you exert a force like this, and then what happens? The acceleration is in the direction of the force. So delta V is like this. So the velocity vector was like this, you add a delta V like this, your new V is going to be like that. And give another pull, you add a delta V like this, perpendicular, so your new V is going to be like this. And you pull, you add a delta V, your new V is like this. Pull, it's going in a circle. Okay? Planet going around the sun, same thing. If the Earth had not been moving when the sun was pulling on it, what would have happened? Just right into the sun. Okay, just like the chair, pulling straight in. If the Earth was moving very, 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 very fast, what would happen? Much faster than it's moving now. The pull in would have worked, but it would have escaped, right? The pull in wouldn't be enough. The circle either would be very big, so the orbit would be very big, or it just would never quite make it, because by the time it turned a little bit, it would be so far away that the gravity would be so small that it wouldn't even feel the tug of the sun. The Earth's orbit comes about because the Earth was moving at a certain speed while it was being attracted by the sun, and exactly the right amount so that it makes the orbit. Those things which were moving but were not at the right speed either escaped or crashed into the sun, or have these big orbits in there. They come around every 70 years or big circle and a small circle, this one starts here and this one starts here. So then it's same everything, direction of velocity, acceleration is the same. 4 seconds later, this one has made it to here, and this one has made it to here. Okay, because they're going at the same speed, and this one covered this much ground, this one covered the same amount of ground, but it took it halfway around the circle, because they're going at the same speed. All right, so at this instant, the velocity is tangential, the acceleration is towards the center, and for this one also, the velocity is tangential, and the acceleration is towards the center, but clearly, none of these are the same direction. Okay, so it's in the same direction in the abstract sense that it's always tangential and always the center, but not in the same direction physically. Right? This one has a higher acceleration, and therefore its velocity is changing more in a given amount of time, so it's making sharper turns, and this one is going more leisurely. They're not really, the direction is not really the same, because at any given instant, one is pointing like this, and the next one is already over here, and it's pointing like that. It's the same direction in the sense that it's always pointing towards the center. But at any given time, right, one is like this, and one is like that. And then when it comes around the second time, it'll coincide for an instant and then pass it.
Okay, so you wouldn't say then that the velocity is the same for the two circles?
The velocity at the top of this one, let's say when you start, is like this, and this one is like this. This one, the next instant, is just slightly dipped. This one is much more dipped. Then this one is like this, and this one is like that. This one is like this one is like that. This one is like this one is like that. At any given instant, right, their velocity vectors are not pointing in the same direction. Until this one completes a complete cycle, and again caught up to this, and again, for an instant it's the same, and then again it passes it. And so on. But they're different circles, and they're going at different speeds, so at the instant when this one is over here, let's say, moving in this direction, this one is already over here moving in that direction. So those are not the same directions, so they're not the same velocities. At any given instant, they'll have different directions of velocity. What will be true about both of them is that their velocities will always be tangential to the circle, and what will be true about both of them is that their accelerations will always be to the center of the circle. But the direction towards the center or the direction on the tangent will be different at any given time for them. Right? Because this one has a direction of velocity along the tangent and acceleration towards the center. At the same instant, this one has direction along the tangent of the velocity and direction of the acceleration towards the center. But those directions are different. I said that the fact that this is moving along the tangent and this is moving along the tangent is the same, and the fact that this acceleration is moving towards the center and this acceleration is towards the center is the same. That's all.
So what's the change? Is
Again, all I'm saying is that because it's moving in a circle, the motion is always along the tangent,
Yeah.
like this,
But the velocity
and the
is always,
acceleration is always toward the center. It doesn't matter which circle you're in.
but the
but-
velocity is the same, though, right?
The velocity of what?
Both of them is
The
equal.
speed is equal.
Oh, but yeah, so there
The
has to be
speed is equal, but the velocity takes into account the direction.
the direction.
So at any given moment, the direction of the speed is different, right? One is here, moving like this, and one is moving like that.
Oh.
The directions are the same only in the sense that it's always along the tangent to the circle. Both of them always move along the tangent circle because they're moving in circles. But the magnitude of the velocity, in other words, the speed is the same. The magnitude of the acceleration is not the same. The one in the small circle, the magnitude of the acceleration is much bigger, right? It's got to make much more sharper. That delta V has got to come in much bigger delta V, or in much less time, right? The acceleration is delta V over delta T. So either the delta V must be a lot bigger to make it a sharp turn, or the delta T must be a lot smaller, whatever, or both, right? Within a given amount of time, it has to be a bigger delta V, or the delta V has to be the same, but in a smaller interval of time, in order to make it turn much more sharp. So the acceleration will be much bigger. All right, now what about the magnitude? We have the direction, so we know that an object which is moving in a circle, okay, even if it's not moving in constant speed, but if it's moving in a circle, then clearly there is acceleration. Clearly the acceleration is towards the center. Therefore, clearly the unbalanced forces are towards the center. Whether it's moving with constant speed or not, if it's moving in a circle, then those things are true. All right, what about the magnitude of the acceleration? We know the direction. What about the magnitude of the acceleration? How would we go about doing that? And again, there's ways of doing this very rigorously, but I want to do it in a heuristic way to kind of develop the equation with you to see the logic of it. Okay, kind of like what we did with F equals ma and what we did with the pendulum. All right, we want to find the magnitude of the acceleration, not the direction anymore, because we know the direction. What should it depend on? What would you imagine?
The change in time, the time that we're changing.
Okay, the change in time. How would it depend on the change in time?
Well, if it's moving the faster, or the less amount of,
But
the less amount of time that it's moving, the faster the acceleration. Or the greater the value.
well, remember that the speed. Let's take the case where the speed is constant.
Okay.
Okay. So now say it again. Remembering that the speed is constant.
If the speed is constant, then it won't be going in a circle.
The speed is constant, but it's going in a circle. But the velocity is not constant because the direction is changing.
Right.
But the speed is constant. It's covering the same amount of distance per time.
Then the time that it completes one rotation is bigger than the less time that it takes to complete one rotation.
Okay. The greater the acceleration or the greater the speed? Or both? Okay, do you understand the question here? Okay, it's moving in a circle. All right. So now how can we compare it? What we do is let's take two circles of different sizes. Okay? And let's take a circle with a given size with different speeds, and we'll compare them and see what kind of acceleration must there be. We'll take this circle, let's say, and a smaller circle. Okay? Now, if an object is moving at the same speed here and here, okay? Right, we can have an object moving with the same speed. Obviously, this one will make more rotation than in the same time this big one is moving 10 or 5, whatever it is, right? But they can be moving at the same speed. This is moving at 50 miles an hour down a big racetrack. This one is moving 50 miles an hour down a small racetrack. They're moving at the same speed. Are their accelerations the same? Okay, what are the two elements of acceleration? What do you mean?
For the bigger circles.
What's it? What are the two aspects of acceleration?
Velocity and time.
Well, the velocity, right, okay, the velocity and the time, but what I meant was actually, in terms of the vector, the magnitude and direction, okay? The magnitude and direction. The magnitude of the velocity, what would you say about it? How would you compare the magnitude of the velocity between these two cases? What is the magnitude of the velocity? What do we call it in English? Speed. Okay. How do you compare the speeds here? They're the same. We're given that they're the same, 50 miles an hour, whatever. So the magnitude is the same. What's different? Or is the direction the same or not? Direction is towards the center, always. But it's not the same circle, but let's say I can put this circle over here, and you can say it's the same direction. But what is different? Why, if they're moving with the same speed in the same direction, then why are they making different sized circles? The radius of the circle is smaller, but why would it be smaller? I mean, it sounds like they should be, they're moving at the same speed and the acceleration is in the same direction. Then why is the circle smaller? Right, you have two cars. You have unbalanced forces on them because they're moving in a circle. They're moving at the same speed, and their accelerations are in the same direction. So, shouldn't the size of the circle be the same? I mean, everything else is the same. Okay, the force affecting, the net force on them obviously must be different. And clearly the acceleration must be, something has to be different. Otherwise, they should be doing the same thing, right? So the answer is the acceleration, the force is greater, the acceleration is greater. Why is the acceleration greater for this circle than for this circle? Was that?
It has to keep it.
I didn't know.
I don't know, I guess it has to keep. Oh, I mean, you need more force to do a sharp turn.
Okay,
As
right.
opposed to-
You're making sharper turns.
Yeah.
You're constantly, this one is screeching, right? It's going around, it's only going 50 miles an hour, but it's going around a very, very tight curve, right? And this one could be going around like very leisurely, right? The change in velocity per time is much greater, right? The change in velocity is much greater. It's a much steeper change, okay? Per given amount of time, this one doesn't change velocity very much. It changes from this to that. In the same amount of time, this one changed from this to that. Okay? You see that? So the change in velocity per time is much greater for the smaller circle than for the bigger circle. And that's acceleration. But the acceleration is much greater. The acceleration is towards the center, and the speeds are the same. But the amount of acceleration is not the same. Okay? So it's very important to keep those. The speed could be the same. The direction of the acceleration is towards the center, and if you put the two circles around the same center, then it's kind of pointing in the same direction. But at any given moment, maybe they're not pointing in the same direction, right? Because this one is, and let's say after 1 second, this one is here, this one is, let's say, went to here. And after 1 second, this has made a complete revolution, so they're moving at the same speed. So the acceleration vector of this one is pointing towards the center, but when this one is pointing like this one is already here, and it's pointing like that. Okay? So in both of them, it's pointing towards the center, but not at the same time. One is making the turn much more quickly, and that means that the change in the velocity vector is much greater and per time. And the definition of the change in velocity vector per time is acceleration. So the acceleration is much greater. All right? So we can see that the acceleration is proportional to what? What was that? Okay? Let's say, what are the factors that it could depend on? It obviously doesn't depend on the color of the car, doesn't depend on the make of the car, doesn't depend on the year of the car, doesn't depend on, I don't know, whether it has 4 tires or 8 tires, doesn't matter. There's a million things that it doesn't depend on. Okay? What are the factors that determine the acceleration?
Force.
Okay, the force is equal to the mass, and acceleration is force over mass. But I mean, in terms of what you see, you're looking at this car going around. What of the factors that you see determine the acceleration?
The distance.
Time.
How big the circle is? You said the time. What time?
Time to make it complete.
Okay. What does that depend on?
Velocity.
The velocity. Okay. So we have the size of the circle and the velocity. What's a measure of the size of the circle? Radius. So we would say it would depend. For example, it's a function of the radius and the velocity. Is there anything else that could depend on?
Can it be friction?
Okay, we're ignoring friction and so on. There has to be friction in order for it to make the turn, but we're ignoring the effect of the friction on the speed and so on. Okay, if you think about it, there's nothing else. I mean, if you know the speed and you know the, in fact, here I don't even need the velocity, it's really kind of the speed. Okay, how fast it's going. If I know the speed and I know the radius of the circle, I know everything there is to know if it's in uniform motion in a circle, if it's going right. If I know how big the circle is and I know how fast it's going, there isn't any other datum, any other fact that I need to know about the motion. Is that true? Is there anything else that I would need to, what else is relevant? If I know how large the circle is and I know how fast it's going, I know exactly where it is at any time. Right? I know everything about it. So these are the only 2 things that could be relevant, and in fact they are directly relevant. The faster it's going, obviously the more it's got to screech, the more the change in velocity has to be in order to keep it in that circle. And the tighter the curve, the more acceleration, and the tighter curve is a measure of the size of the circle, which is given by, for example, the radius. Okay? So we expect that the acceleration will be a function of the radius and the speed. Okay, I'm deliberately writing the speed here. It's the velocity, but we mean like the magnitude of the velocity. Okay, so instead of speed, I can write v with those little bars on the side, which means the magnitude of the vector. Okay? Now, how should they be related? We know that they'll be related to these two quantities. How should it be related? And we have a little experience constructing equations. What would we say? A equals what? It's some function of r and v, or the magnitude of v. How would you do it? Where should, let's say, r appear in the equation? Bottom, because the larger the radius, the larger the radius, the smaller the acceleration. The larger radius, the bigger the circle, the less it has to accelerate. So we expect it to be on the bottom. All right. Where should the magnitude of the vector be? Okay. It's going. The faster it's going, what has to happen? The sooner that change has to come. Okay. Because if it's going very fast and the change doesn't come, it's going to overshoot the circle. The faster it's going, that change of velocity has got to come right now. Right now. If it's going slowly, the velocity vector is going to change to kind of go, okay, now, so to speak. Again, in the limit as the time goes to 0. Okay? So the faster this, the higher the acceleration. So we expect something like this, like the magnitude of the velocity vector v over r. Okay? Let's look at the units now for this equation. Let's look at the units. We have A equals, this is the magnitude. The direction we know is towards the center. If we wanted to be a little bit more pedantic, we would write A acceleration with a little, let's say, R vector here. Because this is a magnitude, this is not a vector. So all this is just magnitude. This gives the vector in the radial direction. Okay? But we're not going to, I don't think they use that in the text. It's just to show you this would be a vector. The vector A, the magnitude, and the direction. But we're going to forget about that in the meantime, and we're just going to worry about the amount. Okay? What are the units here? What's these units? Meters per second. What are these units? Meters. So what units does this come out to be? 1 over second. Is that okay? No. So it can't be this. What units should it be? Meters per second squared. What can you do here to make it meters per second squared? What would you have to multiply? You have to have meters per second here. Meters per second times 1 over second gives you meters per second squared. Right? So you have to multiply by another meters per second here. What would you do to this equation to get that? As you said, make it v squared. If it's v squared, then it's meters squared per second squared over meters, which becomes meters per second squared. Okay? So obviously this is not a derivation. You can't just like do that. Okay? But this is to give you a feeling for the equation. Why it makes sense that it should depend on r and the speed, the magnitude of the velocity vector, and why it should depend in this way with this on top and this on the bottom, and why it makes sense that it should be v squared. And again, this equation can be derived exactly in calculus, kind of exactly using approximations like limit and delta and stuff like that, in algebra, trigonometry, and geometry, and that's done in a kind of concise way in the book. And in my notes, I have a more expanded version of that, and I'll assign it at a different time. Okay, so basically what we found is that something moving around in a circle obviously has acceleration. The direction of the acceleration is towards the center. The magnitude of the acceleration is equal to v squared over r. And remember, it's the magnitude of v, so it's the speed squared over r, but we write it as v squared, okay, without the vector sign. All right, so that's a very important equation. Acceleration equals v squared over r for motion in the circle. Right? Now, it's important to remember that this is not like a force or something like that. It's just when you're moving in a circle, by definition, certain things have to be related to each other. And the acceleration is related in this way to velocity and the radius. Okay, so it's not a law of nature saying that it's a geometrical relationship, kind of. Okay? Now we're going to apply them. The planet Earth about the sun, right? Or a satellite around the Earth is the same exact thing. You have GMM over R squared is equal to mv squared over R. That's exactly the one that we solved over here. Except instead of the Earth going around the sun, they have a satellite going around the Earth. Now, we can write an equation relating F equal to ma for all these cases. All right? What we do is we look at, we have okay, the force on a mass is equal to the mass times the acceleration of the mass. If we're talking about the special case of circular motion, we're talking about a mass m that moves in circular motion, what can we tell right away about A? What do we know right away about A? It's v squared over r. Whatever the velocity is, the magnitude of that velocity squared divided by the radius of the circle, that is the acceleration. I didn't specify yet what force it is that's causing the acceleration, but I do know that if it's moving in a circle, it must necessarily have an acceleration of this amount. So I can already write this side of the equation a little bit differently. I still have no idea. What is the force? Is the force gravity pulling it? Is the force a force of a string pulling it? Is it maybe electrical force? I don't know. Maybe somebody pushing. I didn't specify what kind of force it is. I'm just saying that if it's moving in a circle, it has to have an acceleration given by this. Now, if I'm doing the problem of, let's say, the chair on a rope, all right, so I have the chair here, I have the rope with tension T, and it's moving with a velocity like this in a circle, okay? So there's a tension. What are the sum of the forces acting on this? The only force is, like we said, the tension in the string, so it's T. That's it. T is equal to mv squared over r. T is the tension in the rope. Okay? I could maybe I'll write it, since in this chapter they use T for time, so that's good that you pointed it out. I'll write Ft, force of tension. Okay? What happens if it's gravity acting, pulling in a planet, the gravity of the sun? So I would write force of gravity. And now the mass is not the mass of the chair, but the mass of the planet. And the velocity is the velocity of the planet, and the r is the radius of the planet, of the orbit of the planet, rather than the radius of the chair. But it's the same thing. Force is equal to the mass times the acceleration, where I specify this because I've given that it's moving in a circle. And then depending what the force is, I can use the force and I can solve the problem. That's something if it's moving in a circle, it's moving tangentially along the edge. If it's moving tangentially along the edge, what happens if you cut the string? There's no more forces, and therefore it should continue moving in the direction that it was moving before with the speed that it was moving for. There's no net force, there's no acceleration. The acceleration would have made it move like this. If there's no acceleration, what should happen? The direction and the magnitude should stay the same. If it was moving like this, it just stays the same. By definition, if there's no force, if the sum of the forces is zero, there's no acceleration, means the velocity is the same. If you cut the string, the velocity has to remain constant, which means it goes off like that. Not like that. Okay. 117, he just solves what we talk about the chair, mv squared over r. T is equal to mv squared over r, force. Okay. Example 5.5 on page 118. It's a slightly more complicated example, but very simple. You have a ball not going around like this, but going vertically, all right? And you take a free body diagram at the top and at the bottom of the motion. At the top of the motion, which forces are acting on it? There's only two forces. There's gravity acting down, and there's the tension of the spring acting down. Those are the only two forces. So those two forces added together equals what? M times A. What is A? V squared over R. At the bottom, which forces are acting on it? Gravity down and the tension up. You subtract the two. Which one is bigger? What do you say is bigger? The downward force of gravity or the upward force? How do you know that? If it wasn't bigger, what would happen? If the force was greater down, it would be falling, and as the rope torn and it fell down. It's only if the force is bigger up that the acceleration is inwards towards the center that it makes you move in a circle. Okay, so it's just the same problem, just where you're subtracting two instead of adding. Okay, on page 120. Okay, it's a car going around a curve. That's what we spoke about before. All right, again, the sum of the forces is equal to the mass times the acceleration, where the acceleration is v squared over r. They're all exactly the same thing, except that here you have a friction force. Okay, if you're moving around in a circle, let's say the car is moving in a circle, the driver's turning the wheel. Why does it move in a circle? What will happen if there's ice on the road? It'll keep going, and it'll move, like we said, tangentially. There's no more forces acting. It'll just won't move in a circle. It'll just move straight. Right? The road is curving, and it's going to move straight. What force needs to act on the car to make it move in a circle? That's a force acting towards the center. What force is acting towards the center? Friction. Friction is what's keeping. If there's no friction, it just slides straight. Okay? So that force is the friction force, so you have F is equal to ma, A is v squared over r. Where what is F? Not F is tension, and not F is gravity, but F is the friction force. Okay, so all these problems are the same thing, just with a different force substituted in for causing the circular motion. In one case it's a spring, it could be gravity, it could be... Okay, in example 5.8 on page 121, the complication is that it's at an angle. Look at the diagram. You have a force diagram of the car. All right, which forces are acting on the car? You have gravity down, and what else? Only one other force. The normal force of the road acting on the car perpendicular to it, perpendicular to the surface. It's exactly what we did in the previous chapter, right? You have a perpendicular, it's like the thing sliding down the ramp, the person skiing. You have a normal force going up, and you have gravity force going down. It's exactly the same thing as the skiing, except that in the skiing, the person was going down, here they're going like this. But in terms of the force diagram, it's exactly the same. All right? You break the normal force up into components, and you solve the problem. Where again, you're given that the acceleration is v squared over r. So in a way, it makes the problem simpler. What about the vertical motion? Why are we not looking at the gravity so much?
Because it cancels out
Cancels out with what?
with
With what?
cancels out with the
Why? Okay, why isn't the ball falling down?
because it's spinning.
So, you're right, it's spinning. Why should it be spinning now?
Well, it looks like it is going down.
Okay, right. The force of the tension in the string is greater, approximately. Right. I mean, what do we know? You have this thing is moving in a circle. Okay, there's a mass. We know that there's a force of gravity, mg, going down. Is it accelerating in the up-down direction?
No.
Okay, how do you know it's not accelerating in the up-down direction? It's moving in a circle, and the circle is in some kind of a plane. Now, it's not moving in a circle like, or in a spiral. Okay, it's not going up and down. So the up-down motion is zero. There's no acceleration. There's no motion. There's no acceleration in the up-down direction, which means that there's no acceleration. That what? there's no acceleration down or up, and therefore, what does that mean? What is that? What do we know if there's no acceleration up now?
There's no net force exactly.
Some of the forces in the up-down direction balance out. There's
Yes.
no net force. Okay? But there is a force going down. So what must there be?
And the force going up.
Another force going up. Okay? Whenever you look at this again, just a simple thing. Look in which direction it's accelerating. If it's not accelerating, some of the force is zero. There is a force, there must be a balancing force. What possible force could be balancing it?
The tension force?
Which direction is the tension force? So how could it be balancing it? Okay? So, Karen was saying something? You started to say something about it.
All I can say is it makes a right angle.
It makes a right angle. Okay. The answer is, if there is no tension force pulling it up, then it's going to fall down. There's got to be some force pulling up. All right? But it doesn't have to be, let's say, if you look at the string, okay, you need to have some tension force going this way. It doesn't mean that you need a string pulling in the up direction. You need a tension force in that direction. If I pull on this, on a string, and the string is slightly out of the plane, if the thing is going around like this, and the string is like this, and it's going like that, right? You twirl something often, when you twirl, you can take a piece of string and try it. You twirl it around, it goes around over here, right? You twirl around relatively slowly, it goes like this. It doesn't go like that, right? When do you find that it goes in a circle right around, centered around your hand rather than lower? When it goes really, really fast, it starts going higher and higher and higher. Why? Why is it going faster? What makes it go faster?
You make it okay.
You're exerting more force, right? So why does that, so we can understand kind of why it makes it go faster. Why does it make it go higher?
Black force is more.
Was that?
Black force is more.
Why?
It results.
What? Right, you have, if this is the angle, okay, let's say this is the plane of the motion, and the string is moving an angle like this is the angle theta over here, all right? The tension in the string is here. Okay, that tension has two pieces, this piece and that piece. Most of it is towards the center. What does a force towards the center do, an unbalanced force towards the center? What does it cause? When something is moving already, and you add an unbalanced force always towards the center, what happens? It moves in a circle, circular motion. So this component of the tension force causes it to accelerate in towards the center while it's moving around. While it's moving straight like this, it moves in towards the center. That makes it a circular motion. This component of the force keeps it up. Okay? So you need some component of the force that'll keep it up. Now, if this tension is very big, what can happen? This angle can be very small. If this tension is very large, so it'll be T times sine theta, it'll be this much, right? The bigger T is, T sine theta has to equal what? What does that have to balance out?
MG.
Mg. All right, for small angles, this is small, sine theta. If T is bigger, sine theta will be smaller. Okay? Because the bigger T is, even for small theta, you still have a reasonably sized T sine theta, which can balance G. All right, so the more tension you pull in with, even if it's a small angle, right, it's enough to hold it up. So if you pull enough, it'll look like it's flat. It'll look like it's going exactly around in a circle. It's never exactly flat. It's always just enough of an angle so that it's holding it. Now it's going in a vertical circle.
So gravity is like the string.
Pardon me?
No, gravity is like the string.
Gravity is added onto the string. So when you're going in a horizontal circle like this, gravity is always pointing in this direction, and the tension is always perpendicular to it. When you're in a vertical circle, it's at the top of the circle. The motion is like this. You have the tension in the rope and gravity both acting in. When the thing is at the top of its motion, the string, the tension in the string is pulling it in, and gravity is also pulling it in. It's pulling down in the same direction as the tension in the string. Okay, at the bottom of the motion, they're fighting against each other. Gravity is pulling down on the thing opposite to your tension in the string.
Now, if the only forces that are happening are going straight towards the center, why isn't this
If it's, okay, it has to be moving at a tangential speed in order for there to be circular motion. The force causes an acceleration, causes a change in the velocity, which is a change in the direction, making it like this and like that and like that. If it's not moving at all and you just pull a force in, it'll accelerate straight towards the center. If it's moving like this and you add a force towards the center, it'll move in a circle. If it's not moving, it just falls straight in. Same thing with a body near the sun. If it's flying by the sun, it'll get pulled in. If it's going fast enough, it can escape. If it's not going fast enough, it can crash right in. If it's going right at speed, it'll turn, go in an orbit. Same thing, something going around the Earth. Okay? It has to be moving with a certain speed. If it's not moving with any speed, it just falls straight in. If it's moving with a speed but not enough, it can still fall in. Or if it's moving too fast, it won't move in a circle, it'll just escape. It has to be moving in the right combination of speed this way so that the acceleration exactly just changes the direction and not the magnitude of the speed. Here, we have a combination.
When you say too fast or too slow compared to the gravity, what's the portion of too fast or too slow or too, right speed to make this circular motion?
Okay, there you can do it with equations. It's not in the book, but what it has to do, obviously, you can see, depending on how far it is, the further away it is, the less the gravity will pull on it. Okay, the further away it is, also, let's say the gravity gets very strong around here, up till around here. So this is the danger zone, so to speak. The further away it is, right, in terms of the angle, it'll be more to cover. But in terms of the angle, it's also further away, so there's less force. Okay, but you can compute exactly what speed it has to be so that it'll miss what speed it'll fall in. All right, I can give you a reference to other books if you want, which just develop basically these kinds of equations to compute that. Okay, it could be even one of the examples in the back. At the top, you have both forces acting in the same direction, gravity and the tension in the string. At the bottom, they're in opposite directions. Okay, we're told that it's moving in a circle the whole time. So we know that A is equal to V squared over R, because it's moving in a circle. All right? All right, so the sum of the force is equal to MA. Sum of the forces is equal to FTA plus mg, and that's equal to mv squared over r. Remember, being careful to know which v you're talking about. All right. Now, he says from this equation we can see that the tension force FTA at A will get larger if VA is made larger. Okay. Obviously, for a larger speed, you need to have more tension. But we are asking for the minimum speed to keep the ball moving in a circle. Now, the cord will remain taut as long as there's tension in it. But if the tension disappears, why should the tension disappear? When the speed is very slow, right, you know, it's like if you stop pulling on the tension, the velocity change just falls in, right? You don't have experience doing it. Okay? If you stop pulling on it, it'll just kind of just collapse. The cord can go limp and the ball will fall out of the circular path. Thus, the minimum speed will occur if the force is equal to 0. In other words, you have two forces here. You have the force of the tension on the rope at the top, and you have gravity force. Now, the gravity force is acting perpendicular to the motion. The motion is like this. The gravity force is inwards. right? The motion is along, it's at the top of the circle, the motion is like this. You have the tension in the rope and gravity both acting in. All right, so they're asking, what is the minimum tension that you can apply and it'll still move around in a circle? Now, obviously, the less tension, the slower it's going to move, and so on. No tension at all, why should it move in a circle? Shouldn't it just collapse? Yes, except for the fact that there is another force pulling it in, gravity. Just like gravity is the force pulling the Earth in towards the sun, causing it to move in an orbit, or moving the moon around the Earth, at the top part of the orbit over here, you also have gravity pointing straight in. So just at that point, it's exactly the same as, let's say, the Earth orbiting the sun. You have the force of the gravity between the Earth and the sun pulling it in. But there it's happening at all points. Right? You have the gravity force acting at all points in the circle when it's going around the sun. Here, the gravity force is pulling towards the center where? Only at this top point. At this point, where's the gravity force pulling? Down this way, not towards the center. At this point, it's not towards the center. At this point, it's not towards the center. Only at the point at the top is the gravity force pulling in towards the center. So at this top point, you have the same thing like here. You have something moving with a speed like this. The force is pulling it towards the center. Therefore, it'll move in a circle. All right? So even without any tension in the string, you could have motion in the circle if the gravity force is there. Just over here. Over here it's different. Over here they're fighting against each other. Okay, it's not pointing towards the center. Okay, so at the top point, we'll say the minimum tension is when there's no tension. And it's only gravity that's pulling it in towards the center. And therefore only gravity that's making it move in a circle. So, therefore at the top point, we make the tension equal to 0, let's say. And we have only mg. The only force acting on it is mg going down. That's the only force at this point, no tension. So the force is mg. Sum of the force is equal to the mass times the acceleration. Mass times the acceleration. The force on it is mg, only mg, not no t. And that's equal to ma. What is a equal to? V squared over r, because it's going in a circle. So we have mg equals m v squared over r. All right, that's what they have over here. Mg equals mva squared over r. And you solve for va. This is the minimum speed at the top of the circle if the ball is to continue moving in a circular path. All right? Why does it depend on the speed? Okay, because if it wasn't moving at any speed, what would happen if there was no tension in the force?
Fall straight down.
Fall straight down due to gravity. Okay? If it's moving with a little bit of speed, then it'll move off to the side, not just right. You'll have moving off to the speed, it's moving off sideways at a certain speed, acceleration due to gravity, so it'll fall like this. Just in the regular trajectory that we're used to. Okay? Tied onto the string, so maybe it'll fall a little shorter depending on how long the string is. But either it falls straight in if there's no speed, or it falls with some kind of trajectory like that, constrained by the string if it has a little bit of speed. But if it has the right amount of speed, it'll be moving exactly as a circle, right at the top. Okay. At the bottom of the circle, what happens? There, they're pushing against each other. The tension is up, the gravity is down. So you have the standard case. The force of tension minus the gravity is mv squared over r. Okay, and the Ferris wheel example, you have basically the same thing. All right, response, the free body diagram shown in figure 5.10 is similar to that, for example, 5.5, with Fn replacing Ft. Okay, you don't have a tension force of a string. What is the force on the person? It's the normal force of the Ferris wheel itself. The Ferris wheel is holding it. It's just like a string. Okay. Basically, it doesn't matter if you're whirling the person tied on a string like this, or if they're on a Ferris wheel and the Ferris wheel is pulling them around. Okay, Newton's law tells us that the normal force is less than mg at the top and normal than mg at the bottom. Okay, how do we know that? Why do you see that? Why is the normal force less than mg at the top? How do you know
Because
that?
acceleration is also
Pardon me?
the acceleration.
The acceleration, right. The acceleration is in towards the center. That means that the center-directed force has to be greater than the force going away from the center. The force going away from the center is the normal force. The force towards the center is gravity. So you can tell that if the acceleration is towards the center, that means the sum of the forces is towards the center. That means that the one towards the center is bigger. Okay? And just the opposite at the bottom. At the bottom, the acceleration is towards the center, which means that the sum of the forces is towards the center. That means that the upward force is greater. Okay. Example 5.7. Okay, take a look at it for a moment and then we'll go over it. Okay, what is the situation? You have something moving, a car moving around in a circle, okay, on a circular part of a track. Now, remember we spoke at the very beginning, if I'm walking along here in this room, what is helping me walk? What is allowing me to walk? Why don't I just like kind of moonwalk moving in place? There's friction with the ground. If I were on roller skates, ice skates, blades, right, then I would just be, maybe if I just did this with my feet, I would be just staying in place, right? But because there's friction with the floor, when I move my foot back, I move forward, all right? I'm exerting a force on the floor, the force is exerting a force on me. The force on me causes me to go. All right, if there's not enough friction, if the floor is slippery, then my foot will slip a little bit and I won't move as forward as much. If I want to move in a circle, if I'm running, right? I'm running and I'm rounding the bend, okay? Clearly, if I'm moving in a circle, there's an acceleration towards the center of my circle. All right? There's unbalanced forces in that way. Now, which forces are there in that way? I mean, I'm pushing against the ground this way, moving myself forward. Which forces are pushing me that way?
Centrifugal.
Well, why do you move in a circle? I mean, you're obviously telling your body some different commands to your muscles in your legs if you're moving in a circle if you want to move straight. What you're doing from reflex action, just from as a kid you learn this, you're pushing against the ground, not in a straight direction. You're pushing in the ground partly sideways. You're not aware of it anymore because you, like I say, you learn this when you're a child. But obviously you're doing something different if you're running forward or if you're running in a circle. It's not just random. Something is different. The only thing that's different that's happening is how you're placing your weight and how you're pushing with your feet. How you're placing your weight doesn't help you because if you were running forward, put your weight like this, you'll maybe fall over. All right? But you're pushing with your feet somewhat to the side. Okay, you can try it out at some point, run quickly on a track and see, you'll realize that when you're rounding in a circle all the time, you're giving a certain message to your feet about how to push. You're pushing against the ground sideways, perpendicular to your motion, and the ground is pushing back on you, and that's giving you the force necessary to make the circle. Why are you also leaning? That's what this is all about, like the banking curve and so on. Okay, now, if you're moving in a circle, we know that you have acceleration towards the center. We know that there's unbalanced forces acting on you towards the center. We know that the force is equal to MA, where A is equal to B squared over R. So we know a lot. Just by the very fact you're moving in a circle, we know half of the solution to the problem. Okay, now, you have the car moving on the track. Okay? It wants to move with a certain speed around that track. So we know we're given the V. We're given V of the circular motion. It's moving in a circle, we're given the V. So we know that if we square that and we have the radius over the R, that's going to be the acceleration. If we know its mass, we can multiply in, that's the force. So once we're given the radius of the circle and the velocity with which it's moving, we already know what force is going to be necessary putting a perpendicular force on it. Something is going to be having to be putting a perpendicular force on it. Now let's say you have the capability of putting that perpendicular force. Let's say your feet are capable of doing that, but the floor is slippery. You're just not going to be able to do it. Okay? So here you have a car moving with a certain given speed around the track where the radius of that curved part, if it were a full circle, it's not a full circle, but it's, let's say, a track that goes like this, but at this point it's a circle. So at this point the motion is circular motion. Okay, so you know everything. You know the velocity. You know the radius. What you need to know is there enough friction force? Okay, because the friction force between, not between my foot and the floor, but between the tire and the tar, is what's going to govern whether or not there's enough force for you to be moving in a circle over here, sideways force. All right, so you have to make sure that the friction force, which is some proportion of the normal force, is enough. And that's what this problem is. The next problem, you have something interesting. You may have noticed on certain highways when you're turning the bend that they're banked. How many of you have ever ridden on a banked highway? Okay, the highway turns like this. All right, it's like instead of the road being straight flat like this, it's like this. The car is moving like this, but it's a circle. Okay, you can see racetracks sometimes the highway turns like that. In bobsledding it turns like this. Why? You have a force. Okay, it's going. Let's say you have the car is moving along this. Do you see what this is? This is like an inclined plane, but it's extending out like this in a circle. So the car is moving like this on the inclined plane. Okay, do you all visualize that? You have gravity force acting down. The normal force that this thing can push, the surface can push against the car is always, by definition, it's a normal force. Normal means perpendicular to the surface. We choose now, let's say this is our x-axis, this is our y-axis. What force is there downwards?
Gravity.
Not exactly gravity, but a component of gravity.
Yeah, that's why.
Okay, in downwards I'm talking about now in the minus y direction. Okay, depending how I choose my angles, if this is my angle theta, so it's mg cos theta. If this is my angle theta, so it's mg sine theta. Okay, so I have mg, the cos theta, sine theta, depending how I chose my angle, in this direction. It's at mg sine theta. Now, where is the circle that it's moving on? It's moving on this circle, like that. Okay? Right? See that? It's moving, if this is the inclined plane, where is the circle? It's moving along the circle like that. Okay? So, what is the force moving towards the center of the circle? It's a force in that direction. You have a normal force component in this direction and a normal force component in that direction. All right, this normal force comes there because gravity is pushing in, and part of the component of the gravity, in other words, you have the car is on this, the car is on the plane, all right? It's pushing into the plane and down. Gravity is pushing it down. Let's look at the plane like this. It's pushing down. Part of that gravity force is pushing into the plane, and part of it is pushing it along the plane. Okay? The part that's pushing into the plane is responded to, all right, by the normal force. Now, if you break the normal force into two components, you have Fn cosine theta and Fn sine theta. Okay? Which component is pushing the car into a circle in terms of its circular motion? Okay? It's not the component along the plane. It's not this. Okay? Because the circle is not like this. The circle is like that. You see that? The circle is not, this is not the center pointing towards the center of the circle. It's not moving like this. It's moving like that in a circle. So this is the force pushing it towards the center. Okay? And that is Fn sine theta. Okay? If this is the normal force, then this is a component of that. Alright? So that Fn sine theta has to be large enough. That's the force that's pushing it towards the center. That's the one that has to be large enough to make it move in a circle. Alright, so just like we had before in the previous example, we had the friction pushing it in towards the center. This is the force pushing it in towards the center. Okay, and then we just have that component equals mg squared over r. Okay, example, section 5.4 and 5.5 we skipped. in section 5.6, you have just some plug-in problems. Example 5.11, right? You're just doing F equals G M over R squared. Okay, just a simple plug-in. Same thing in example 5.12. Just basically a plug-in problem, and also 5.13. Okay. You should be able to do those easily. 5.14 also, just plugging in. All right, so you should be going over all these examples, being able to solve them well. Look over the laboratory. We went over in 2 separate classes. Okay, look over a little bit of the rest of the experimental procedure. We'll do it in combination with some other lab. Okay, I want you to be able to, as though we had done the lab this week, I want you to have reviewed whatever we spent almost an entire class on that example. All right, to review it and look at the laboratory procedure, that when we get to do it, it'll just go very, very quickly.
What are we doing in lab?
We'll do the actual lab itself in combination with another lab, but what we did in the last class and the one before that, basically we covered the whole lab. In theory, all we have to do is just the measurements, adding a few weights on either side. You should be able to know exactly why we're doing it, how we're doing it. We spent a lot of time on that. Just read through section 4, the experimental procedure, so that when we actually do it, it shouldn't take more than a few minutes.
But that'll be.
If anybody's interested in additional reading, not for credit, there's nothing to do with the course, but it's a book that's very, very nicely written. It's become a classic in the last, 20 years. Deals with quantum physics and general relativity, all kinds of very, very interesting ideas without any equations whatsoever. And you don't even need this course background to read the book. Don't think people have read the book without studying any physics before. It's called The Dancing Woolly Masters by Gary Zukav. I checked in the library. It's all the way in the back, on the left, in the stacks QC 173.98. If you don't have extra time, don't bother with it. It's also available. It's in paperback. It's available in any good bookstore. There's 2 or 3 copies of it.